If a modern human stepped out of a time machine into an Ice Age forest in Europe and came face to face with a Neanderthal man, the first reaction would not be anthropological curiosity. It would be a gut-level jolt of recognition mixed with unease. This was not a stooped brute or a shaggy cartoon caveman. This was a human, but built on a different physical template, one that would make even trained modern athletes look slight. Thick neck, deep chest, arms like bundled cables, hands like clamps, face carved in heavy ridges and planes. Not a monster, not an ape, but something that looked unmistakably like a version of us engineered for a harsher world. If the Marvel Universe needed a biological inspiration for the Incredible Hulk, Neanderthals would be a better model than fiction ever admitted. Their Hulk-like appearance was not about height. Many Neanderthals were shorter than modern humans. The shock came from mass, density, and structural power. Their skeletons were not simply larger copies of ours. They were constructed differently. The long bones of the arms and legs had extraordinarily thick outer walls, the dense cortical bone that resists bending and impact. The internal marrow cavities were often relatively narrow, meaning more bone tissue per cross-section. In engineering terms, modern human bones are lightweight aluminum tubes designed for efficiency. Neanderthal bones are more like reinforced steel pipes. That difference changes everything about how a body handles force. Muscles anchor to bone, and the places where muscles attach tell a story. On Neanderthal skeletons, those attachment areas are often massive. Ridges and roughened surfaces on the humerus, radius, femur, and pelvis indicate repeated, powerful use of the same muscle groups over years of life. Their upper limbs, especially, were built for torque, leverage, and sustained force. When researchers analyze the cross-sectional geometry of Neanderthal arm bones, they find patterns associated with heavy asymmetrical loading, the kind you see in people who do intense manual labor from adolescence onward. Except in Neanderthals, this is not an occupational niche. It is the species norm. Strength, then, was not an add-on. It was baked into their developmental program. A Neanderthal did not need a gym or structured training to build a powerful physique. Their growth trajectory, combined with daily survival demands, produced bodies that modern humans rarely approach outside elite strength sports. But this strength was not the sculpted aesthetic musculature of a bodybuilder. It was functional density. Thick forearms, powerful shoulders, wide backs, compact lower limbs. They were not optimized to run marathons across open savannas, as early Homo sapiens were. They were optimized to grapple with their environment directly. That environment was unforgiving. Ice Age Eurasia was a landscape of cold, fluctuating climates, long winters, and large, dangerous animals. Neanderthals hunted bison, horses, deer, and occasionally even mammoths at close range. Their weaponry, especially earlier in their history, emphasized thrusting spears rather than long-distance projectiles. To drive a wooden spear tipped with stone into a struggling animal at arm's length is not a clean, cinematic action. It is violent, chaotic, and physically punishing. Every hunt risked broken bones, goring, trampling. The fossil record bears this out. Healed fractures, rib injuries, head trauma. Neanderthal skeletons often look like the medical files of rodeo riders. Yet many individuals survived serious injuries long enough for bones to heal, indicating both resilience and social care. This brings us to endurance, but not the modern notion of endurance as distance running. Neanderthal endurance was about tolerating cold, fatigue, and sustained physical effort under load. Their bodies were compact, with relatively short limbs and broad trunks, a shape that conserves heat. Large nasal passages and sinuses helped warm and humidify frigid air before it reached the lungs. Their overall mass meant higher caloric needs, but also greater capacity to generate and retain warmth. Living in such bodies meant constantly burning energy, hauling carcasses, processing hides, gathering fuel, and moving through rugged terrain. Their endurance was the endurance of labor, not the endurance of speed. Speculation about hormones often enters the conversation because Neanderthals show traits that, in modern humans, can be associated with androgen exposure: heavy brow ridges, robust jaws, powerful muscle attachments, strong sexual dimorphism. Some researchers have proposed that Neanderthal skeletal growth may have been regulated differently, perhaps with a distinct relationship between androgens and bone modeling. But this does not mean Neanderthals were the equivalent of modern humans with pathological testosterone levels or on steroids. Pathological hormone excess in our species leads to health problems, bone issues, and reduced stability. Neanderthals, by contrast, represent a stable evolutionary pattern lasting hundreds of thousands of years. If their endocrine system differed, it was an evolved baseline, not a disorder. The impression of high testosterone is therefore better understood as a byproduct of their overall developmental design. Their bones grew thick. Their muscles loaded those bones heavily from youth. Their faces and skulls followed growth trajectories distinct from ours, with forward-projecting mid-faces and strong brow ridges that may relate to biomechanics and respiratory adaptation as much as to hormones. What looks like hypermasculinity to modern eyes is, in many respects, a different architectural solution to the same human blueprint. Fearlessness is another trait often attributed to Neanderthals, but this too must be interpreted carefully. They lived in a world where hesitation could mean death, from predators, from cold, from hunger. Natural selection would favor individuals who could act decisively under stress. Their hunting methods alone required a willingness to approach large animals at dangerous distances. Yet the archaeological and fossil evidence also shows care, cooperation, and social bonds. Individuals with serious disabilities survived for years, suggesting group support. Fearlessness, then, does not mean reckless aggression. It means a behavioral profile tuned to high-risk subsistence in a harsh environment. Pain tolerance likely played a role in this world. Repeated injuries, heavy workloads, and exposure to cold would have shaped both physiology and psychology. While we cannot measure Neanderthal pain thresholds directly, their healed injuries indicate that they endured significant trauma and continued to function. Modern humans in industrialized settings often live in bodies cushioned from such extremes. In comparison, Neanderthal daily life would feel brutally demanding. Their normal would be our crisis. Their hands tell a similar story. Neanderthal finger bones are thick, with strong joints and evidence of heavy gripping. The outer fingers, especially the ring and little finger, were built to stabilize powerful grips. This supports the idea of repeated forceful tool use, hide processing, and weapon handling. Yet they were not clumsy. Their thumbs were well developed, and archaeological finds show they produced sophisticated stone tools and engaged in tasks requiring fine motor control. Their hands combined power and precision, but with a clear emphasis on load-bearing. All of this, bones, muscles, hands, chest shape, adds up to a body that modern humans instinctively read as formidable. But the Hulk metaphor, while vivid, can mislead if taken too literally. Neanderthals were not superhuman in a comic book sense. They were not invulnerable, and they eventually disappeared as a distinct population. Their strength came with costs: high energy demands, heavy reliance on large game, vulnerability to environmental change. Modern humans, with lighter frames and greater emphasis on social networks, long-distance mobility, and technological innovation, followed a different adaptive path. The evolutionary hypothesis, linking higher testosterone levels to survival traits, including enhanced night vision, is a fascinating area of research that draws from various fields, including anthropology, evolutionary biology, and endocrinology. In ancestral environments, traits that increase survival and reproductive success would have been favored by natural selection. Higher testosterone levels are associated with increased muscle mass and strength, which could enhance hunting and foraging capabilities. Elevated testosterone levels can promote risk-taking, which might have been advantageous in competitive or dangerous situations, such as hunting or defense against predators. The link between testosterone and night vision is more speculative, but can be understood through several mechanisms. Testosterone influences various physiological processes, including those affecting retinal function. Rod cells, responsible for low-light vision, require certain nutrients and metabolic processes that might be enhanced by testosterone. Some studies suggest that testosterone may play a protective role in retinal health, which could enhance the ability to adapt to low-light conditions. This might include effects on retinal cell survival and function, leading to better night vision. Higher testosterone levels might correlate with heightened sensory awareness and responsiveness to environmental stimuli. This could be beneficial in low-light conditions, where quick reflexes and heightened senses would improve survival chances. There's an evolutionary hypothesis that suggests higher testosterone levels could be linked to survival traits such as enhanced night vision. In ancestral environments, better night vision could have provided an advantage in activities like hunting, which may have driven the selection of traits associated with higher testosterone and improved low-light vision. This connection might also hint at broader evolutionary adaptations, where enhanced testosterone levels and improved vision in low-light conditions could have provided survival advantages to early humans. However, the direct biochemical relationship between testosterone levels and low-light vision is still a subject of ongoing research and remains to be fully understood. Early humans living in environments with varying light conditions, such as those in northern latitudes, may have experienced selective pressures that favored individuals with traits enabling better adaptation to low-light environments. Individuals with enhanced night vision may have had advantages in foraging or avoiding predators during dusk or nighttime, leading to higher survival rates. In addition to physical survival, higher testosterone levels may have played a role in social dynamics. In social species, including early humans, males often compete for mates and resources. Higher testosterone levels can lead to more competitive behaviors, which may have resulted in greater reproductive success for individuals with enhanced night vision and other survival traits. Traits associated with higher testosterone, such as physical strength and confidence, might have been attractive to potential mates, further reinforcing the link between testosterone levels and survival traits. The evolutionary hypothesis linking higher testosterone levels to enhanced night vision and other survival traits provides a compelling narrative about how physiological and behavioral adaptations may have influenced human evolution. While direct evidence linking testosterone specifically to night vision remains limited, the broader connections between hormone levels, physical capabilities, and survival strategies offer valuable insights into the complexities of human adaptation and evolution. Further research may illuminate these relationships, revealing how ancient survival pushed evolution. Modern humans inherited some genes related to vitamin A metabolism from Neanderthals. These genes could have helped early modern humans adapt to different environments by influencing how the body processes and utilizes vitamin A, which is crucial for vision, immune function, and skin health. The real lesson is not that Neanderthals were exaggerated brutes. It is that human evolution has explored multiple physical strategies. One path emphasized endurance running, long-distance projectiles, and lighter skeletons. Another emphasized close-range power, structural durability, and cold resilience. Both are human, both are intelligent, social, and culturally capable. If we see Neanderthals as Hulk-like, it says as much about our own softened, technologically buffered lives as it does about them. Strip away heated buildings, supermarkets, vehicles, and medicine, and place a modern human into their world. Suddenly, the Neanderthal body does not look extreme, it looks appropriate. Thick bones to resist fractures, massive muscles to handle constant labor, compact shape to conserve heat, hands built to grip, scrape, thrust, and carry, a physiology tuned to pain, risk, and physical stress. What seems extraordinary in the modern world may have been simply what survival required. So the image of a Neanderthal as an Ice Age Hulk is both wrong and revealing. Wrong, because they were not mindless engines of rage or walking hormone imbalances. Revealing, because their anatomy reminds us how flexible the human form can be under different selective pressures. They were not caricatures. They were a parallel expression of humanity, one forged in cold, danger, and direct engagement with the physical world. And if we met them face to face, we might feel small, not because they were monsters, but because they carried in their bones and muscles a version of human strength we have largely left behind. Thanks for watching.